Hello everyone and welcome to Vibrations and Acoustics. Today we're going to do another example of just a standard spring mass system with a forcing function applied to it. Okay, so the way we get started up with this, we need to find the response for this system based on these initial conditions. What you can do is you can derive the particular and the homogeneous solution for x of t. X of t is equal to xh of t plus xp of t, which is the particular and the homogeneous solution for the equation of motion. But when you see just a basic spring mass system and you're looking for the response of it, you can actually skip right to a basic equation of motion based off the information that we have. We know that this is cosine. So the only thing we have to do is remember, or hopefully we have an equation sheet. You can skip to this equation of x naught minus f naught over k minus m omega squared cosine of omega n t plus x naught all over omega n, x naught dot over omega n of sine of omega n t plus f naught over k minus m omega squared cosine of omega t. And this equation is basically this equation after you've found the equation of motion. Now what you can do too is you can go up here, you can say, okay, well I have this mass and I've got k acting in this direction, I've got some weight acting in this direction, and I've got the forcing function acting in this direction, so f of t, kx, so on and so forth, and you create the equation of motion from this block, and then from that equation of motion you find the homogeneous solution and the particular solution, and those will combine to give you this equation. But if you see a forcing function of the form 400 cosine, then you can skip right to this equation. And if you have a 400 sine, then you reverse this cosine with a sine, this sine with a cosine, and this cosine with a sine. And then you solve it from there. So it's really pretty easy to just keep this equation around, or keep it in your head for this situation, and say, oh, I don't even have to find the equation of motion, I can just skip right to this equation. So that's what we're going to do. If you want to practice deriving this equation, you can go ahead and do that, but it is an equation in most vibrations book that is presented to you to use to find the response of a spring mass system. Okay, so now, for the situation of our ICs, all we have to do is sub these two values into this equation, and the values that we all have up here. Before we have to do that, though, we also have to find omega and omega n, which I forgot to mention, omega n. So omega n is equal to the square root of k over m, which is going to equal 4,000 all over 10 square rooted, which is equal to 20 rads per second. Rads per second. So that's your omega n, and your omega is given. It is actually this 10 right here, because this equation is equal to the form of f naught cosine or sine of omega t. And that's the form of this equation, so there's your omega, which is the 10t. Okay, so now we have omega and omega n. We can solve these all into this equation, and if you go ahead and do that, you get x of t is equal to 0.1 minus 400 all over 4,000. The 400 comes from this, again up here, which is your f naught is equal to 400. F naught is equal to 400. Okay, back down here, 400 minus 10 times 100 cosine of 20t plus, and I'm actually going to carry this off down here because it's kind of long, plus 400 all over 4,000 minus 10 times 100 cosine of 10t. Okay, and of course the x naught over omega n, x naught is equal to 0, so this goes away, and then it cancels out, so you just have these two terms. Solving this, you should get negative 0.033 cosine of 20t plus 0.133 cosine of 10t. And that will be your response for this system under these initial conditions. And then if you have other initial conditions, you can basically just solve that, plug them into this equation too, and resolve again. It's pretty easy after that. The main trick is seeing this equation and realizing, oh, it's a spring mass system. I have a forcing function of this form, a simple sine function, basically, cosine or sine function. I can just grab this equation and plug all the values right into it. Or if you want to go the long way, you can do a free body diagram, find the equation of motion from the free body diagram, and then derive this equation from the homogeneous and the particular solutions. And I've done 1 or 2 examples of how to do that in the past. Hopefully you can check out one of those videos and find out how it works.